So my background is a little different. I come from a developer background. I started as a developer in a company in India, and I worked on an ERP product on the HRM side of things. So this product was actually for the US government, and it was something like SAP, but for the public sector. So it was really complicated Java application with really difficult build cycles, and it took a long while for us to actually write code and actually bring it to the customers. And then I moved to NetApp, and then I kept working on Java still, and I worked with different applications like Oracle or database applications, and worked on solutions which worked around backups of these applications. I understood all NetApp storage features, snapshots, clonings, and things like that during this period. So that's where I got introduced to the infrastructure side of things. And then I moved to Munich, and I learned about SAP. I worked on all our integrations around SAP. I wrote plugins for SAP HANA. So that is the kind of background I have, which is more developer focused. And that's why now I moved to this role where I can understand what developers go through and have a different kind of perspective than an infrastructure guy. And today, we are going to talk about applications and application data. And to build on top of what Andrew talked about, containers and how containers are actually helping application developers, we are going to talk about what data these applications have. And then we are going to see how Kubernetes is handling with its features, with its different APIs, how they're handling these features and how they actually implemented using persistent storage within Kubernetes. So when I say application data, what do I mean by that? So application data could be just an object store where you could store media files. So that is more kind of an unstructured kind of data. And then it could be relational databases or transactional kind of data, which you store in a database, right? So these are the two kind of high-level distribution or classification of data that I can do when I'm thinking about an application, right? So, but we are going to focus more on the side of databases and applications which actually store data. The main purpose of these applications is actually to maintain data for the user, right? So these I would call stateful applications. And today the talk is about, does it make sense to actually run these applications within containers? And what kind of features, what kind of technology is already available for us to run databases or key value stores or NoSQL databases under containers? So that's basically what it is all about. It's very technical. We will actually look at different concepts of Kubernetes, like volumes, persistent volume claims, storage classes, and stateful sets. So there are lots of new keywords probably for you that we will try to understand and see, okay, how does Kubernetes handle all this? So why are we talking about this? Why does it make sense to actually run applications like databases under containers? You can standardize your deployments with YAML or JSON files. You can make it repeatable, right? You can do easier HA deployments of your applications. You can also do scale out of applications such as NoSQL databases, right? So these are the kind of things that we get from actually containerizing databases. So now we will get into actual technical concepts within Kubernetes and try to understand what does Kubernetes offer for these applications or applications which need persistent storage. So first concept that we have today is a concept of volume plugins in Kubernetes and the concept of volumes as such. So Kubernetes understands all these different types of volumes. So you can see we have cloud storage here, Amazon EBS, we have Google Cloud Engine, persistent disks, we have NFS and iSCSI, right? And we also have something from the open source community, which is Ceph RDB, and also Cinder, which supports OpenStack. So there is a wide variety of storage that Kubernetes already understands. And on every Kubernetes node, there's a process which is called kubelet that runs. And this kubelet is actually responsible for providing the application which runs as a pod. A pod is actually a set of containers which are actually interdependent or which share one host. Okay, so basically we can just consider pod as our container or a set of containers. And kubelet is responsible for providing this volume to the pod. So kubelet understands all these storage types, and is able to provide storage to the pod. So this functions already, and that is how you do it today. And let's look at some examples of how you would do that. So this is a YAML file which is used to deploy applications within Kubernetes. Okay, so you can see I have a pod which uses API version v1, and it is an Nginx pod. So basically, it's a web server that I want to run, which exposes a port. And this is how I provide volume to my pod. So I'm defining exactly within my application, which is my pod, how the storage should be attached to my application. As an application developer, I need to understand probably how iSCSI works and what kind of connection details probably my storage admin has provided me to actually use this storage in my application. But you can see that this particular volume is part of the application itself, right? And we have another example, which is from Cinder. And you can see that I'm providing just a volume ID. So basically, you can configure something like cloud provider in Kubernetes, and then you can directly use OpenStack volume IDs within your pod. So that's how volumes and volumes plugins work in Kubernetes. So whatever kind of volume you have, NFS, iSCSI, you can actually provide that details here, and then it will function or will be mounted to your application. So what we just saw is actually dependent on the pod. The application developer is actually providing the volume within his application. But like we have compute resources in a cluster, right? We also want to provide application developers with storage resources. So there comes new concepts where you can have pod-independent volume management. Okay? So now we will learn two more concepts. The first concept is persistent volumes. So what are persistent volumes? They're nothing but a set of network storage, which a cluster admin will provision for the consumption of application developers in the environment. Okay. They are independent of any pod. So I do not think about an application when I'm actually provisioning this storage. I'm just provisioning it because it's a resource that I want to provide for people who are actually using my cluster. Okay. It could be NFS, iSCSI, or any other cloud kind of storage. And this is an example. So here I have NFS. We looked at iSCSI, but this is a new example where he's just providing an NFS server and the path to the volume, so to say. So he's just saying that this is a volume that exists or is available for the developer to consume. And it is 5 gigabit big, and that's it. So he will actually provide that to the developers. Now to consume this storage, a developer needs to create something called a persistent volume claim. And that is something like a request from the developer. Okay, I need storage for my application, and I want to create a claim for that. And I provide different things like how big it should be, what kind of access modes I need for that, and something called reclaim policy, which we can go in detail later. But this is basically a request for storage by the application developer. Now, this is an example of how a persistent volume claim looks like. So you can see, as a developer, I'm providing the access mode and how big my volume should be. And in my application, I'm providing that claim itself to consume that storage. Now, what we just saw is basically static provisioning. A cluster admin is actually going to create different kinds of volumes in the environment. And then application developer will come in and actually use persistent volume claims or create requests and consume this kind of storage. But there is one more way in Kubernetes, which is very new. It is dynamic provisioning. So how do I provide self-service for these volumes so that a cluster admin doesn't need to basically pre-provision these storage, and I can actually use these storage or create this storage on demand. So that is something called dynamic storage provisioning within Kubernetes. And now we will actually compare these two and try to understand how these two ways of provisioning storage or providing storage within Kubernetes works. So let's review again what static provisioning is. So in this case, I have a user, I have a cluster administrator, and I have my Kubernetes cluster. Okay? And the cluster admin has access to the storage system, in this case, NetApp SolidFire. And the cluster admin will actually create PVs. So he will deal with persistent volumes as an API, and he will create different kinds of storage that will be available in this environment. A developer wants to consume storage, and he will create persistent volume claims for his application pods and say, OK, I need this storage. So this is a request. Then something called a PV controller in Kubernetes comes into the picture. And it is monitoring these persistent volume claim requests from the user. And it is going to actually map them with one another. And then this storage will actually be mapped and be available for that application to consume.
Have the developer and the admin had to talk about this? Or the developer just asks for one, and Kubernetes gives him or her one that meets the requirements that they asked for?
So it could be different in different scenarios, right? So it could also be that it's a cloud environment, and the developer itself is a tenant. For example, if he's operating in a Google Cloud Engine, he could actually run his own APIs and be the cluster admin, for example. It could also be the case that the cluster admin doesn't talk to the developer, and he just pre-provisions lots of different kinds of storage and makes these different kinds of storage available for the cluster, and then they are just mapped to the request. So it's not fixed how you consume it, but there are different options that are available. So in this case, if we think that the cluster admin is not talking to the developer, and he has provisioned something 10, which is of the size 10, and the request which is coming is 8 gigabytes, so the mapping happens, but it is not really the right mapping because there's a mismatch. But it is able to fulfill the request. This could be 100 gigabytes here, but still the mapping will happen, but we will lose storage. So this is not the best way to actually provision or provide storage in Kubernetes. Now, we will start talking about dynamic provisioning in Kubernetes. But before we actually do that, we need to understand the concept of storage classes. So just think, as an administrator, you have access to different kinds of storage systems or different kinds of storage. And you want to make these storage available to your developers or users of the cluster. And you want to abstract all the complexity underneath the storage systems or the features that they provide or different kinds of disks, for example. So they can provide or define something like gold, silver, bronze, or production, development environment, or staging environment, and they can actually kind of create a storage catalog for the users. It could also be something which is dependent on quality of service levels, which the storage system already provides, right? So basically defining different types of storage within the environment. And how you do it, basically, in this case, this is an example with NetApp Trident, which we will talk about in a bit. I'm just saying that it should be a SolidFire backend, and it should use NetApp's provisioner. So we will go in detail about this later. But basically, an administrator can actually define these different kinds of storage within the system. So now let's look at how dynamic provisioning works within Kubernetes. So we have the same environment. We have the cluster admin. We have the Kubernetes cluster and the user. But now the cluster admin is actually going to define storage classes. He's going to say, OK, I have a storage system which can offer IOPS or guaranteed IOPS, and I would like to create different storage classes depending on that. So here in this case, it's SolidFire, which offers that feature, but it could be different storage systems which have different kind of features that I want to expose. But here I'm using IOPS, and I create this catalog. So once I've created this catalog, one more thing as an administrator I need to do is deploy a provisioner, something which will help me actually provision and talk to the storage system. In this case, it will be NetApp's Trident provisioner, which will help provide this dynamic storage provisioning in Kubernetes. So once he has done that, we can actually remove this cluster admin from the picture. So he doesn't exist anymore, and he can actually go get a coffee and not worry about this environment. So he can lose his control.
So would Trident take care of things like, for example, if we have to do VLANs or if we're dealing with iSCSI or anything like that?
So handling iSCSI is already implemented within Kubernetes, which is as part of the kubelet. So we already have an iSCSI plugin. What Trident will do is actually provision the storage and provide this in the Kubernetes cluster as iSCSI LUNs. Okay. And then kubelet will be responsible for mounting. For example, if a pod dies at one host and then restarts on another one, it will take care of mounting the storage from one to another.
Gotcha.
I'll briefly toss in that it also applies if you're using ONTAP with NFS as well. right? So the expectation is the consumer of those storage resources doesn't really have to know or care. Trident provisions the volume, it hands it back to Kubernetes as a standard PV at that point. Kubernetes manages the connectivity to the host where the container is being executed at.
So networking guys don't need to get involved, generally speaking.
Generally speaking, right, the expectation is that the network as well as the access method, right, so be that a volume access group in SolidFire, be that an export policy, right, an I group and ONTAP, all of that's already pre-configured, right? It's simply attaching that volume to the requisite hosts. So again, coming from a VMware background, right, think of this as all of the hosts in my cluster have to have access to the shared storage.
Yeah.
Same principle.
Yeah.
So once this is set up and the cluster admin is out of the picture, now the developer comes into the picture and says, I need storage for my application. So he creates, he still uses the same product, same API, which is persistent volume claim. He creates a claim, and Trident is monitoring these claims and checking out, okay, if there is something that a developer needs, and it does create a volume on demand, so to say. So this is kind of more self-service oriented. And once it is provisioned, then PV controller comes into the picture again and actually does the mapping for the user. Right? So this is how dynamic provisioning works in Kubernetes. So NetApp is not the only platform which supports this. Kubernetes comes with its own provisioner, which supports Cinder from OpenStack, all kinds of cloud storage, GlusterFS, and Ceph RDB. So basically, you can think that when I'm using Kubernetes, it doesn't matter what kind of platform I'm using, right, underneath. If it's OpenStack, if it's a VMware environment, if it's just accessing iSCSI or NFS directly, or accessing cloud storage itself, right? So it's able to understand and provide different kinds of storage for applications. So here I would like to introduce what NetApp Trident does and what it actually provides. So NetApp Trident is actually a provisioner within Kubernetes, and it will actually monitor PVCs, storage classes, and it will help you define storage classes within the environment. And once you do that, it will talk to the storage systems and provision storage for you. So that's the basic functionality that it provides. And it itself runs as an application or a pod within Kubernetes. So it's not something which is running on a VM, separate VM or something like that. It actually runs as a Kubernetes application itself in a container, right? And then you can use different kinds of storage features like compression, disk types, or IOPS, and then make these storage classes and offer them to the user.
Running as a container itself, do you have a chicken and egg scenario then? If
so
it needs to be up, obviously, for the other container
Kind of like
to be able to provision.
vCenter.
Right.
Yeah.
So yes and no, right? So
It depends.
Yeah, it depends.
So Kubernetes doesn't need Trident in order to function, right? Trident is only fulfilling the role of provisioning and destroying persistent volumes. So if Trident is not available inside of the cluster, more or less the only thing that is lost is the ability to provision new volumes.
Okay.
PVs that are released or PVCs that are released resulting in a PV being deleted, it'll just go into a queue, right? Likewise, if I put in a PVC while Trident is down, it'll just sit in a queue and it'll wait and it'll retry periodically until Trident
So it's just a management plane, not part of the data path,
Precisely.
not part of anything else. Once it's built, it's built.
Precisely.
Okay.
Right, so we do recommend, right, so right now it is a deployment in Kubernetes, which means that it is a container running Trident. If something happens to that, Kubernetes itself takes responsibility for reinstantiating it somewhere. Right, and we simply rely on an etcd instance, either associated directly with Trident or an existing one that may be maintained. I encountered a customer recently that their database team runs the etcd instance. So whatever they happen to use, if they have an existing etcd instance, we can simply point at that.
So are we going to get, let me go next. Are we going to get into like replication, things like that, or is that something that Trident does, or is that still reliant on the native NetApp?
So you're still relying on the underlying storage platform for
Okay.
things like replication.
Okay.
So replication is something that we are very aware of the desire for. The
Right.
problem is it's extremely complex to transparently do replication, right?
Yeah.
So at an engineering level, we're evaluating a number of ways to not just how does it work best with NetApp's platforms, right? Because great, we could say always have a replication set up between these two ONTAP clusters or these two SolidFire clusters, right? But that doesn't work for the broader community.
Exactly.
Right, so how do we architect this? How do we engineer this so that upstream, right, in Kubernetes, we can define something that represents replication and then allow the underlying platform to actually implement
Exactly.
that,
Yeah.
right?
So that Trident would probably fill that.
Hopefully, right? That's our goal, or either hopefully we define it upstream, Kubernetes.
Exactly.
Trident simply acts as a provisioner. Now maybe that's, and I'm being completely facetious here, right? I'm making this up as an example, right? Trident has two different storage classes that are defined. Kubernetes says, okay, provision in A, now replicate to B, right? And then Trident simply understands how to implement.
How to map those out.
Do you see Trident as a long-term solution, or is one day we're going to have a multi-storage platform Trident-type solution where if I've got NetApp, I've got Dell EMC, I've got whatever, I'll be using that instead of Trident? How do you see that?
Andrew's personal opinion is that I believe Trident will be more long-lived than, so yes, the upstream will have its definitions, right? I hope that Trident becomes that platform as a model for what this looks like. It is completely open source. We actually leverage Docker volume plugin code on the back end, right? Which means that theoretically, even though our competitors are not rushing to give us equipment, right? Theoretically, we could take basically any storage that has a Docker volume plugin, test it, validate it, right, surface up those capabilities, and then be able to provision those volumes off of that.
Yeah.
Yeah.
I mean, it's an interesting discussion, right? EMC did Viper, right? And it was going to be this multi-platform, cross-industry, blah, blah, right? Okay, it does great with EMC gear. Nobody else cares because EMC owns it. That's the question is, can we get beyond that manufacturer-specific layer for these types of provisioning and management?
Absolutely.
We
So
could have the same discussion with the EMC code guys. They're building.
Yeah, I mean, I'm not painting anybody in a bad light.
Rexray.
Yeah.
I think honestly, each manufacturer or vendor will probably end up having their own. And I think there'll be some cross compatibility, like with Trident being
Yeah.
able to run EMC gear. I think that seems natural that'll evolve.
Yeah, I just hate to get back in the VMware days of different plugins for different arrays with different settings and different things and different variations.
Yeah, but doesn't that feel a little inevitable though?
It does. That's why I asked the question. Trying to be optimistic
Yeah,
for
let's
once.
not go there
It's not
again, right?
working.
Just imagine that I'm running a Kubernetes cluster in Amazon,
Yeah.
and I'm running a Kubernetes cluster in my data center, and I've defined 3 storage classes. It doesn't matter for the developer what underlying storage is, right? If it's SolidFire or if it's Amazon EBS, he just sees these storage classes and he's able to, we are able to abstract everything with these provisioners. So even if I have 2 or 3 provisioners, I can just deploy them also very easily using just a YAML file. It's not that it's something I need to deploy in the previous world. It's also a very, very different kind of deployment today. And if I have 3 provisioners that I have, and I have 3 different kind of storage systems, I can just add them to one YAML file and just deploy them and configure them. I think it's much easier to do that. And then same I will do in Amazon, and then it's seamless for the developer, so to say. And that's what we're actually going to see now in the demo, as to how the developer consumes this and actually writes an application.